Welcome in. So let's dive into basically four problems which are related to kinematics, the use of the equations, being able to substitute, keeping in mind kind of the vector notation, so positive, negative, ensuring that your direction is the same, and being able to kind of take a graph and then dissect it and break it down and hopefully try to rebuild, okay, from the graph various velocities, accelerations, or vice versa. So here's the first example, okay, that we're gonna dive into. So the first example is this one. Now, given the following equation, so this is a displacement equation that is given. It's one of the hardest ones and longest ones that you actually have in foundational physics. So given this one, let's take a look at part A. So for part A, it says we want to be able to find what the displacement is. Now, the displacement itself, so we have the equation right there. So I'm going to just copy it, paste it down. It's going to be a set of my givens. So I have the following formula, and I am looking basically to try to solve for this, which is going to be the displacement in total. Now I want it in meters, and I want the direction to be east. I'll worry about the significant figures at the end. Now they give us all of this information. So they say that we have the initial, okay, so notice we have the initial velocity. So this one is 3.8 meters per second. Notice this one is east. Okay, so this is exactly what I want in the question. So I'll keep it that way. I have the total change in time, which in this case is 8.8 seconds. And there is obviously no direction here because time is a scalar. And then we have the average acceleration right there. And that is equal to 1.5 meters per second squared. Notice it's west. So I want it to be east. So I'm going to change it to east. But if I do that, then be careful because you're going to have to change the actual sign. So if you change the direction to be opposite, remember you have to negate whatever the magnitude was. So this just designates for us, okay, so what is happening with the actual acceleration. So let's take a look and see how we can break it down in terms of an answer for this. So if I substitute all of this in, what I'm going to get is, so this is going to be my delta D, okay, is equal to, so I can just sub in. Now notice all the units, so meters, meters, and then everything else is seconds. So that is consistent, which is exactly what we want. So we have 3.8, so I'm going to drop the units, and the direction is the same throughout. So now next, so 8.8. And then it's going to be, so plus 1/2 the acceleration, which is negative 1.5. And then the time, okay, that I have in there is going to be 8.8, and it is squared. All right, so I have all of this. So now I can just substitute, put all of this into my calculator and see what it will give me. So this is 3.8 multiplied by 8.8. Okay, so that's going to be the first one. Now, I'm not going to round anything here yet. Now, that negative, I'm going to put that right in front. And then I'm going to get, so 1/2, which is 0.5, times 1.5, and then times 8.8, and that is squared. That is 8.8 squared. Okay, so that will be 58.08. Now, if I take this, so 33.44, and then minus, this is 58.08 that I have equals, so this becomes negative 24.64 east. All right, now that negative, so this is a good indication for us. So because of this, it looks like whatever this was moving, it was kind of starting off to go east, and it started to decelerate, and then it started to go back. All right, so the negative means that you're actually on the west side. So you're 24.64, and this would be meters because we were dealing with meters, and east. So it is the same thing as saying 24.64 meters west. Now they wanted it in east, so we'll keep it in this way. Now be careful with the sig figs. So they said 2 sig figs. So if you're going to be rounding this off, so I'll keep it right here. So this is going to be negative, and this is, I guess, 25 meters east. And that would be your answer. And it's just a test if you can take the given pieces of information, ensure that the directions are the same, and then substitute them back in. So that's part A. All right, so now let's dive in and maybe take a look at part B. So in part B, it has the following. So it is utilizing the same formula, and now we're supposed to be finding the average acceleration, and we want it north, right? And these are the given pieces of information. All right, so I am just looking at all of this information right here in B. All right, so, I'm going to kind of steal this again, just so that I have it handy as I need it. Let me bring this back down, so paste it, and I'll use it as I need it. Now, the given pieces of information, so what do I have? Now, if I scroll back up, so my displacement is 150 meters north. So I have my displacement, 150 meters north. And this is what I want to keep my direction at. So notice right there, that's the direction that I want, so north. Then my initial speed, or the initial velocity, is 2.5 meters per second. But notice that one is south. So I have to be careful there. And so that's going to be my initial velocity. And that initial velocity, so it's 2.5 meters per second. Now it's south, so I'm going to change this. Now if you change it to north, then it's going to be negative 2.5 meters per second north. So that sign just simply changes back. And finally, we have the total displacement, the total time, which is 25 seconds. So all the units are fine. We have all meters, we have all seconds, so that's all fine. The only problem was that we kind of had to be careful, okay, with the unit right there. So just change it to north if that's the direction that they want. So change everything to the direction that they're asking you for, and then you can go ahead and proceed. All right, so now substituting all of this in, now that all the directions are the same, so this is going to be 150. Units are fine, so I'll drop them. So I'm just substituting into the equation. It's going to be negative, so 2.5, and this is going to be the time, which is 25 seconds. And now this is going to be plus, so 1/2. I'm looking for this acceleration. I'm going to just write it as A, right? So I don't have to write the vector and the AVE, so I already know that everything is north. So that's fine. And it's going to be just a little bit of a shorthand for me. And then this is 25 squared. All right, so now let's try to go ahead and proceed and see what it gives us. So nothing to do on the left-hand side. Now I have to multiply, so this is going to be 2.5 times 25, except it's negative. So this is negative 62.5. Then I will take, so I have that half, so half is 0.5, multiplied by 25 squared. So this is going to be plus 312.5a. Now don't round yet, okay? So we're going to be rounding at the end. So just keep them as they are. So now I have to isolate and solve. So I have to be comfortable in solving for this a. So I'm going to be moving this over to the other side. So that's going to be 150 plus 62.5. The sign just changes. And then I have 312.5a. And so that will be 150 plus 62.5. And that is 212.5 equals 312.5a. All right. And now dividing both sides. So it's going to be 312.5. And this will be divided by 312.5 right there. So now that you can do that division, so that will get rid of this, and you're going to be able to solve for your a. So I'm going to take that answer divided by 312.5, and that's going to be 0.68. Okay, now they've asked for two significant figures, so this is it. And I'm going to just kind of move this out of the way so I can put the unit, which is meters per second squared, right? So it's an acceleration. And then this would be north. All right, so that's what this was. And that is it for this example. In this second example here, you are basically getting tested on the utilization of the formula. So you have a formula on the left-hand side, you have your final speed, and then on the right-hand side, you have your initial speed, you have an acceleration, and then you have the displacement, at least in its magnitude. So when you're dealing with this one, notice that this is just magnitudes. There is no vectors here. It won't be a problem. So when you're utilizing this particular equation, just make sure that all of the directions are the same. And then you can substitute just the magnitudes within it. So let's dive in and try to see. So they're asking us for the initial speed here. And they want the initial speed in meters per second, and they want it east. So we have to kind of make sure that everything is in the east direction so that we don't have to worry about any of the vectors. So they are indeed all east. So if you've noticed that something was west, just change it, its actual sign, okay, and then utilize it that way. Now, let's kind of take a look and see what happens as we're going to be substituting all of these. So what do we have given? So our pieces of given information, so we have our final, and that is 10.2. Notice it's meters per second right there. I'm not going to write the directions anymore. They have the acceleration, the average acceleration, and that is equal to negative 1.0, and this is meters per second squared. So everything is in meters and seconds so far. And then we have, okay, the delta D, and that is equal to 85 meters. So again, so that's all consistent on the unit side. So we can just go ahead and substitute it back into the formula. So within the formula, we're going to be using this one right here. And all I'm going to do is I'm going to take all of the givens and then substitute them back in. So let's do that. So on the left, this is going to be 10.2, and it's going to be squared. On the right-hand side, I am trying to find what this initial speed is right there. So this VI. And now, as you're kind of moving along, so this is going to be plus, and this is 2, negative 1.0, and then the delta D, which is 85. All right, so this is what I have. Okay, so now let's go ahead and find out what this is. So 10.2, this is going to be squared. So that's going to be on the left-hand side. So 104.04, don't round anything yet. On the right-hand side, well, it's going to be 2 times negative 1, so that's negative 2. Okay, so I can just go negative 2 and then times 85. All right, so this is going to be VI squared, and this is going to be minus 170, okay, as we're going along right there. And so now as you're progressing through this, okay, so let me shift this out of the way. So that's negative. Now we want to be able to bring this over to the other side. So that's going to be 104.04. The sign changes, so this becomes positive. So we have that. And then we have VI squared right there. All right, so this is what we would have as we're going along. So now that 170 and the 104, so I'll just keep everything as they are. So there you go. So that's going to be 274.04 equals. And now we have to take the square root, right? Because we have the square over here on top. Sorry, I just deleted it. Okay, so we have the square over here, and we have to take the square root of the answer. So what does that mean for us? Well, what it means is that VI is going to be equal to, and this is going to be the square root, and this is 274.04. All right. Now, of course, when you take the square root, the answer could be both positive or negative. Okay, because if you square it, you're going to get 274.04 back. So just be careful. So let me clear this out. So 274.04 equals, so that's going to be VI is equal to 16.55, 4, etc. Now, did they tell us to round? Let me just double check here. They didn't. Okay, so we don't have anything to round or significant figures, so always just round to the least amount. So it looks like, right here, this one has 3 sig figs, this one has 2, this one has 2. So I'll just keep it at 2. So that's going to be 17. So that's going to be 17, and this is meters per second. Now, as I said, because you can take the square root, so it can be both positive or negative within here. But as we're kind of moving in the east direction, so we're going to take the positive amount. Okay, so this is going to be the positive result within here. So that would have been 17 meters per second. Okay, and it would have been east. And if you can think about and visualize what is happening within here. So if you had, if this was your direction, and let's say, you're moving east right here, okay, then what happens is, so it looks like, you started off moving it around approximately 17 meters per second. And now notice the acceleration, right, which is east, but it's negative. So it looks like, you're slowing down, and eventually you're slowing down to 10.2, meters per second over here. So somewhere, so you've covered this distance. Now that distance is your delta D, which is equal to 85 meters, right? So that's the distance from that side, from one side, so from here, okay, all the way up to here. That would be the distance that you've covered, and the negative acceleration means that you've been actually slowing down, moving in that direction. So this definitely does make sense as you're moving along in here. So there you have it. Okay, so that's your answer if you were just plugging it all in. When in doubt, you can just take the positive. But if you have more context, if it's a word problem, then obviously you can find out a little bit more. Here, this is just playing around with a formula and getting comfortable in moving your terms and factors all the way around. Okay, so that's another example for you. Okay, so this example, okay, this is basically a graph which is given, and we want to be able to sketch. Now, if it's meaning sketch, so it doesn't have to be perfect, but we can certainly sketch this out. So we have a position time graph. So notice the vertical is D, it's meters, and it's on the east side. And then, on the horizontal, we have our time. So this is a position time graph, and we want to be able to sketch the velocity time graph from this. And then we want to shift over to acceleration. So now please don't forget, if you're going from a position time graph to a velocity time graph, then really you're just looking at the slopes, right? So you're just looking at the slopes throughout. So there's really 4 segments here that we have, okay, that we can work out in. So we have this particular segment, so that's going to be segment 1 between 0 and 2 seconds. Okay, we have our second segment, so that's going to be this, which is between 2 seconds and 5 seconds. We have a green segment there, which is I'm going to call number 3, so between 5 and 8 seconds. And then we have our final segment, I guess, and that's between 8 and 12 seconds. So I'm going to call that 4. So that 4 is going to be the easiest one because it looks like your position doesn't change. So obviously your slope will be 0, and then so will your acceleration. So really the hardest part will be 1, 2, and 3. So let's dive in and try to see how we will do this. Now, before you start sketching these out, so in an actual graph, just do the actual kind of calculation of the slope, find out the details, and then sketch it out for yourself, kind of how it looks like, and then you can transform it as you need. So that you can kind of know what the numbers are that you're going to have to put. The horizontal, which is time, that's never going to change, right? So it's going to be the same time intervals. But the vertical, because you're moving to velocity and then to acceleration, they will change because it will just depend on what you're doing. So let's begin. So number 1, so I'm going to do the first one first. So when you have this, you basically 3 things can happen, right? So you either have a position time graph which is flat, so you're basically stuck at the same position. You have a straight line, okay, so you have a constant change, so you have a constant speed, Or as you can see here, you have a curved, and that means you have been accelerating. So notice that whatever this is, it has started off, okay, from -10. So now if this was, if this is east, that means it's 10 on the west side. And it starts off, and if you wanted to find out, so within here, so notice this looks like if you have, because you're going to put a tangent line right at the point of the start, so that would be right there, and it's basically a flat line. So that flat line means that initially you started at -10, okay, east, or 10 west, and you were basically not moving at all. Your speed was just 0, and then you started to take off, so you started to accelerate. So the first thing that will happen is that your initial, okay, velocity that you will have in here, this is going to be right here, and that's going to be just 0 meters per second. So that's what you're going to have initially, because it's just a flat line. Now the next thing that happens, okay, so this is the only thing that you have to worry about, is the initial point and then the final point. And then you can just connect it, because in position time graphs, they always, even if they're accelerating, okay, so they're accelerating in a uniform acceleration. All right. So you have this one, okay, so that's the first one you need. Now the next one that you need is your last one. So that's going to be, so you need to put in, okay, a slope which basically kind of goes in, and this particular slope has to align. So now this is going to be easy for us, because at the end point, notice that it's going to be aligning exactly with the slope right above. So the end point right here, so this slope that you have, you can actually find out what this is. I'm going to just shift this out of the way. Now slope, remember, is rise over run, okay, within here. So this looks like it goes right nicely in, okay, so this is the tangent line right there. And you can now find any 2 points that you like, right, and calculate this. But I'm going to calculate it from here, so from the second one. So I'm going to kind of knock down 2 birds with 1 stone. So because of the fact that the slope at that point, the tangent line, is going to be identical. Okay, so my rise, okay, is going to be, so if I take this out, okay, right there, let me just kind of go up. Whoops, that's not what I wanted. Okay, so let me shift this out of the way. So what do I have here? Okay, so I have, so this is going to be my rise over here. Okay, and then my run over here. So I have to check. So that means, from this point to this point, right? So I want to know that rise. And notice on the left-hand side, so if I map this out, notice it's 5 and this is 10. Now this looks, because it's a graph, so 1, 2, 3, 4, 5. So it looks like it's ones. So this is really 6, right? So this is, okay, if I wanted to put this in there, this is 6. Now, this point right here, as I kind of shift it over here, this looks like it's a 4, right? So this basically is just going in from right there, sorry, from 4. It's -6. So let me just kind of go back in here, because I forgot that it's negative, right? So we're going, so notice 0, then it's 1, 2, 3, 4, -5, -6. Right, so that's where it's -6 right there. So it went from -6 to 6. So that's a rise of 12, right? So 6 minus -6, which is 12. And then the run, okay, so this is in time. So it goes from here. So notice between 5 seconds and 2 seconds, right? So this is 3 seconds. So this is 12 meters and 3 seconds. So that's not very difficult to be able to calculate for us. So the slope, which is rise over run, 12 divided by 3, that particular slope is just simply 4 meters per second. So this is what we have thus far. Okay, so what we've done is, let me just kind of shift this back. Okay, actually I'll just leave it there. So that means that my final, okay, now my final, this is for the first point, so this would have been 4 meters per second that I have in there. Okay, so that's what I would have. And that 4 meters per second, okay, is the velocity at that time. So how would this look like on a graph? So if you were plotting this out on a graph, so between 0 and 2 seconds, now this is only sketching, I'm going to combine it at the end. So this just means you started from 0, okay, and then you're going to have a straight line on your velocity, right, time graph, and it's going to be, this is 4, right, so this is going to get all the way up to 4 right there. So that's that first stretch. Now that second stretch, this one, so from here all the way to here, this is a straight line, which, as I told you, because it has the same slope as this, right, as you can see there, right, they align exactly at that point. So they have the same slope. So I've already done that calculation for number 2, and it's a straight line going up. So I need to know what that slope is, because remember that the velocity is the change in your position, right, divided by the change in time. So that's what happens. And that means that for number 2, so as I'm going along here, so for number 2, there's nothing really here to do, because your v is just simply equal to 4 meters per second, so that it continues. So again, if I'm sketching this out, so this is, if I continue this all the way through right here, so if maybe I'm going to draw it out a little bit further. So now this goes all the way up to 5, and what this would mean that it stays there. So it's just a straight line. It's a flat line, okay, right there between, so 2, okay, and this is going to be 5. So the velocity kind of is increasing, right? So that's what we see over here on the between 0 and 2 seconds, and between 2 and 5 seconds, it is flat, all right? Now, the next item, okay, so that's going to be number 3 right there. Now, we already know what the velocity here is. This is 4 meters per second because we just got there. Now, this is going to make our life very easy, as you can see. So although there's a curve, all I need to know is what is the velocity at this point. But, I mean, as you can see there, okay, so this curve, right, so it just curves nicely, and then it just flattens, okay, and then it's just a flat line. So if you were drawing and you were trying to draw a tangent line, well, that tangent line is just a flat line there, okay, that you would have. And flat line, well, we know what the slope of a flat line is. So the slope of a flat line is 0. So it looks like this is speeding up, okay, keeping the same speed, and then it starts to slow down. And it starts to slow down. It's still moving in the east direction here, as we can see, but it starts to slow down to basically a stop, right? So it starts to, slow down, and so that means that is between 0 and 8 seconds. Okay, so this would be right here. This is 8 seconds. And this just goes from 4, and then it slows down, okay, and this goes all the way to 0. And then for the remainder, so for the last component, okay, that you see there, okay, so what you have in that last component, you can see, so let me just kind of take this out of the way right there. So that is that fourth component. So I'm going to remove this. That fourth component is from right there to right here, so up to 12 seconds. And you can see we're staying in exactly the same position. So it looks like we're stuck there. It looks like it's 12 meters, okay, and we're just not going anywhere. So that means that here, this would have been just a flat line, right? Because it has a slope of 0. So there you have it. So that's how your actual sketch would look like. And now if you want to make it a lot prettier, you certainly can, right? So now you can take this and you can expand it, make it bigger, okay? So you certainly can do that for this. So if I can take this right there, I can certainly take this down here and make it a lot bigger, okay, and then clean it up, so make the lines nice and crisp. But this is what the sketch would be. So the only thing that might be missing, that your teachers might want, is this is time in seconds, right? This is your velocity. This is in meters per second right there. And this is on the east side. All right, so this is what you would have. Okay, so you're moving in the east direction, okay, as you're going through. Now, if you want the acceleration, right, so now as you're kind of moving over to the acceleration graph, okay, so for your acceleration graph, now I'm going to do a little bit of a better job, hopefully. Okay, so I'm going to kind of map it out, okay, into the same thing. So how would this look like? Okay, so this is your acceleration versus your time. So this is your time in seconds. This is going to be the acceleration. This is going to be in meters per seconds squared. Well, now you're going to have also, once again, 4 points, right? So you're going to have 1, 2, this is going to be 3, and this is going to be 4. So you have 4 different sections. So if you're lining them up, okay, so section number 1, again, so going from velocity to acceleration, you're looking at the slope because acceleration is equal to the change in velocity divided by the change in time. So it's the rise over run. And now in this case, you know, you can see there, right there. So your rise, this one is much easier. So from here to here, the rise is 4 meters per second. The run is 2. So 4 divided by 2 is 2. So that means that for the first section, okay, right there, between 0 and 2 seconds, this is going to be just a flat line, right? So this is just 2 meters per second squared. Now, your second part, it's a flat line. So the slope of that flat line, okay, so right here, it's going to be literally a flat line. So maybe I'll draw it from here. Now, as I go here, you know, I'll put, you know, we can put this dot and then we'll put a little empty dot so that we can draw this. So it's going to be from here and then up to 5 seconds. So it's a flat line, all right? Okay, so that empty dot that you see right there, okay, just means that we can't have the same point in 2 spots, right? So you can't be in 2 places at the same time, right? So that's all that is saying. So that means you can't have 2 different accelerations at the same time. So now as you're moving along, so that green piece, okay, so that's this one right here. So for that green piece, what you have, notice it's a negative slope. So you are falling 4, but your run is 3, right? So you're going from 5 to 8. So that is 3 seconds, okay? And then you're falling, so notice you're going from 4 down to 0, right? So that's going to be -4 divided by 3, right? Which is your answer. So that's a negative amount, okay? So this is going to be somewhere from here, okay, to over here. So this is your negative amount there. Let me put a, okay, so empty spot there. And hopefully it's a flat line in there, okay? And this value is -4/3, right? So you can put it as decimal if you like. I'll just leave it as -4/3, and it is meters per second squared, all right? So this would have been kind of the deceleration side on this. And then the last one, so once again, so it's a flat line. So, you know, as you're moving along all the way up to 12, okay, so this one you can't put the 2 dots. So you're not accelerating at all because you're not moving. You're in exactly the same spot. So that's how this sketch would look like. All right, so this is the sketch of this particular example. That is it. So here's another graph, except this one is now from acceleration, and we want to be able to go from acceleration in reverse. So we want to get back into velocity, and then we want to get back into position. All right, so you know, how do these particular graphs work? So this is all based on calculating the area. So if you recall, if you go from position, velocity to acceleration, you're always looking at the slope. If you go in reverse, you're looking at the area under the curve because you want to know what the change is. And they do give us kind of the initial starting points. So this is good so that we can kind of go back. All right, so this is acceleration. Okay, so we can calculate what the acceleration. Now we have three kind of points. So we have one, okay, so we're going to have one area. So that's going to be, we have to find out what this area is. Okay, so that's going to be the change in velocity that we have. Well, the second one is very simple. So this is number 2. Well, the change, so here, okay, is going to be 0. And then we have a third one. So that's going to be this area right here. And this one is also not very difficult. So these are just two rectangles that we have to deal with. So that's very easy for us to find what the area is. Okay, so for number 1, so this is how we would proceed. So let's find the area first. So as you can see there, it's 1.5. So we have 1.5, so that's at the top. And it stretches out for 4 seconds. Okay, so 1.5 meters per second squared times 4 seconds. So notice we're going to get, this is going to be 4. So this gives us basically 6, right? So this is 6 meters per second. That is the change in velocity, okay, that we have. Okay, so that's the first one. The change in velocity for the second one, we just said this is 0, so we have nothing to do there. And then the change in velocity over here, so the last one, so this is another rectangle. Now notice this is going to be negative, right, because it's on the negative side. So this is going to be the change in velocity is equal to, so for this third piece, and that's going to be just simply negative 0.5. I'm just reading it from the graph there, so this negative 0.5 right there. And then that stretches out from 8 to 12, so 4 seconds. So this looks like it's negative 2, all right, meters per second. That would have been the change right there. I'm kind of disregarding any significant figures or anything like that, because this is simply just a sketch that we want to get a concept of what is happening. Okay, so now if you want to graph this out, so now I'm going to just sort of make it too big. So let's make a little bit of a better job, I guess, or try to. All right, so we're going to try to map it out. Okay, so, you know, here, I'm going to drop this down. Okay, this is going to be at 4 seconds. Okay, here, I'm going to drop this down. This is going to be at 8 seconds. Okay, and then here, well, you don't have to do that, but it's just so that it kind of matches up. So this is your time in seconds. Now, we are trying to find what the velocity is. Okay, and then you can put here meters per second, because that's what we had. Okay, so now, they told us that initially, so notice we started off at 0, right? So now we're north. I guess acceleration was on the north side as well. So you can certainly put north over here. So 0 means, we started off from right here. Okay, this is our initial spot. So this was initially, okay, at 0. All right, so that's at 0 right there. And now the change, so notice that what we had is the change was 6 meters per second. So that means, okay, so it's going to change, your speed is going to change during that whole entire time. So it's a consistent change throughout here. And it's going to go all the way up to 6. So this is going to be 6, okay, meters per second. All right, so this is 6 meters per second. So I'm going to put this. Now you put that all the way at the end. Okay, so this is where it's going to end up. And now you can connect these, all right? Now, think back, right? If someone gave you the actual velocity time graph, which, would be this, how would you get the acceleration? You would have to take the slope. Well, what is the slope? Well, it rises for 6, right? And it runs for 4. So 6 divided by 4 is 1.5, which is exactly what we had over here. So it was 1.5, okay, right there. So that's what we have throughout this one, all right? Now I noticed that actually this is an empty dot, so I'll keep that empty over here as well. Okay, so let's delete this thing and put an empty, okay? And so now as we're going to be continuing on, okay, so now we have our initial. Now the change for the next one is 0. So that means, okay, it actually, it starts over here and it's not going to change at all. So it remains, right? So within here, so this remains at 6 meters per second because the change was 0. The area was 0. And then finally, okay, so for the last one, so notice it's negative. And so what would we do for this one? Okay, so for this one, we're starting off. So now we know, okay, that our initial one is at 6 meters per second and our change has been negative 2. Well, 6 minus 2 is 4. So it's going to end up, okay, at 4. So this is going to be right here. And if you were plotting it over here, so this is now going to be at 4 meters per second. And it's going to go all the way down. So it's going to look like this. And you're done, right? So you have now mapped out the velocity time. And if you look at the slopes and you calculate the slope for each region, you're going to get your acceleration back, right? So notice you've dropped minus 2, right? So minus 2, and then it went from 8 to 12 seconds. So that's right here from 8 to 12. So that's 4 seconds. And negative 2 divided by 4 is negative 0.5, which is exactly, okay, what the value is over here. Okay, so there you have it. So now you have a sketch of this. Now you just need, so for the final one, okay, you're going to need a sketch to go back from the velocity to the position time graph. So now once again, you're going to need to know and figure out what the areas are. Okay, so now you're going to have 3 things. You're going to have 1, you're going to have 2, and then you're going to have 3 areas. Now these ones are not as nice as the previous one to find the area, but it's not a big deal, right? So the area over here, it's a triangle, so that would have been 1/2 times the height, which is 6 meters per second, okay, multiplied by 4, right? So that's, notice if you look at the units, meters per second times second, it's going to be just meters. Well, 6 times 4, 24, divided by 2, which is 12 meters. So what is this? This is the change, okay? So that's the change that we have in your, so that's the kind of the displacement, right? That's what we would have. It would be a change, okay, in position of 12 meters. Okay, so that's that. Now for the second one, so this one, what is the change over here? This one is a rectangle, so much easier. So this is going to be just 6 multiplied by 4. So this is just 24. So that's 24 meters, and that is your change in, this second one. The third one, so this one, what is the change overall? This one's a little annoying. Okay, you can break it down into 2 pieces, if you forget. So you can break it down, okay, into a triangle, so right here, and then you can break it down into a rectangle. So let me just erase this, all right? So here's your triangle, right there. So that particular triangle, so notice that this is going to be 1/2. Going up, it's 2, right? And then running for 4. There's going to be tiny displacement coming in from here. So that's going to be just 4 meters. But now you also need, okay, that rectangle. And in that rectangle, so that is going to be at 4 multiplied by, and this is 8 and 12, so that's also 4. So that's going to be 16 meters, all right? And that's this. Okay, that's this rectangle right here. That's 16 meters. And then the triangle is 4 meters. So in total, if you add them up, okay, so that one is going to be 4 and 16, which is 20 meters. So that would have been your final displacement. All right, so now that you have these, what do you do? Right, so like how, what's going to happen here? How does this kind of look like? Now, okay, whenever you're accelerating, so this is something that, you should be aware of. So if you are going to be, okay, so as you can see there, so that's on the first, okay, on the red one. So you're accelerating, so notice it's positive, okay, it's in the north direction, right? So you're basically kind of speeding up over here. You went from 0 to 6 meters per second. So how does that look like? So if you were graphing it, it always is going to look like this, right? So it's going to look something like this, okay? So it's basically kind of like a parabola, like a quadratic, where it just kind of skins over. And then if you were doing your tangent line, so the tangent line over here, that would be 0. And if you did this tangent line over here, that would be at 6 meters per second, right? So that's what you want to be able to see. Okay, so that's the first one. The second one, because it's just a flat line, okay, so that's what you have there. Now, what is that telling us? It's telling us that we have a constant speed of 6 meters per second. Okay, well, a constant speed of 6 meters per second, so that means, okay, this is going to be just a straight line, right, going at 6 meters per second, okay, that you have, and it's a displacement of 24, right? So it's going to be just a straight line. Now, we're going to be connecting all of these things together, and I'll do that in just a moment. And then the last one, okay, so notice you went from 6 meters per second to 4 meters per second, right? Now, this doesn't mean you're going down in position. You're still moving, okay? However, you are going from 6 meters per second, so you're kind of like this, and then you start to curve, okay, a little bit. Now, this one's going to be harder for me to do, but it's kind of going to start looking like this. But you're still moving in the north direction. And really, now what we want to do is we want to be able to connect all of these kind of together, right? So this is kind of how it's going to look like. That's that graph. So let's do that on the side and then, kind of properly write it out as a sketch. Okay, so we have, so this again, this is kind of up, right? Now we know that we're going to be all in the positive side. So this is my t in seconds, all right? And now I want to say, okay, so this is at 4, this is at 8, and this is at 12. So I'm just matching it up. And now, what am I going to be starting from? Okay, so now I have to kind of take a look and see. So they said, notice right here, our initial position was negative 20 meters north. So it's actually on the south side. So I was wrong. Okay, so here, let me just kind of go back and place this down. So your starting position, okay, is negative 20. Now, our first displacement, right, okay, notice, is 12 meters. So during this stretch, we went 12 meters up. So that means, okay, so as you're kind of going up 12 meters, well, negative 20 plus 12, we're going to end up at negative 8. Okay, so somewhere over here. Okay, and this now stretches out all the way to here. So that's from here to here. And how does it look like? It's that kind of, a curve that you have, okay, in there that looks kind of like this, right? So this is this curve right there. All right. Now, next, what we have is, now as we're continuing, so we're going to displace 24 meters, right? And it's positive. So we're going to go from negative 8 and then 24 up. So, so negative 8 plus 24. So we're going to end up at 16. So our position is 16. So now, okay, we're kind of moving along here, and we're going to go all the way up to 16. Might run out of space here, but okay, so it's going to look like this. So this one, okay, we're done. All right, now we know that it's going to be a straight line, okay? Okay, so now this is going to end up, okay, so somewhere over here, now it's 16, right? So this is our position. This is in meters, okay, and that's north. So we're going to end up at 16 all the way over here, right? So this is 16. That's the total displacement over there, and it's a straight line to that. Okay, so that's how this would look like. So that's another one gone. Now the last piece, okay, 20 meters. All right, so well, I have kind of run out of space here, but okay, I'll do this and shift it down so that you can see it, and then I can kind of cheat a little bit. So that's why it's good to calculate them first. So within here, so I'm going to kind of shift this back up. And this is going to go up another 20, right? So 16 plus 20 is 36, all right? So that's what you're going to have. So this, okay, is going to go all the way up to 36, okay? And, you can write it out. So this is going to be, again, this is just a sketch. So here, this is the point, okay, 36, okay? And it kind of starts to go like that, where it's not a straight line exactly, you know, so it's basically a line and then it starts to curve. So initially, this slope over here was at 6 meters per second, but this slope over here, okay, is at 4 meters per second. So notice that that's what happened over here. It went from 6 to 4. And that would have been your sketch overall. All right, so there you have it. So that's another example. Thanks for watching.